Okay, probability worked exam questions, mainly tree diagrams, but a few other bits and pieces at the A and A star level for higher maths. Probability of bias coin landing on a head is 2/5. Basic tree diagram, 3 marks of filling in a tree diagram. First task to get ahead is 2/5. Basic rules of tree diagrams is all the branches in one section must add up to 1, so these two branches must add up to 1, so we know that's 2/5. This has got to be 3/5. The coin does not change its probability the more times you throw it, so it's just going to be the same again on the second toss, heads and tails, and the same again, heads and tails. There'll be 1 mark for getting these two right, 1 mark for these two, and 1 mark for these two. Okay, slightly harder question. 10 different names are put on a computer. One of the names is Jaspal. On Monday, the computer chooses 2 names at random. The computer is set so that the same name can be chosen twice. Show the properties Jaspal is chosen at least once is 19/20. Now this at least once type probability is actually a quick way of doing this, but I'm going to do the long way first. So let's just look at the whole thing. So we're choosing between Jaspal and not Jaspal. I'm going to represent that not Jaspal by a dash. And again, Jaspal, not Jaspal, Jaspal, not Jaspal. So that's our tree diagram. This is the first time round, and this is the second time. And on a there's 10 different names, and each one's equally likely. So Jaspal has 1 in 10 chance of coming out, and everybody else would add up to 9 out of 10. There's 9 other people. The computer set so the name can be chosen twice, so the name goes back in the hat if you like, so it's the same probability again the next time, nothing's changing. So these are all the same. So, where's Jaspal chosen at least once? Well, it's chosen twice there, once there, and then not once, and then once there. So those 3 would give you the answer, so 1/10 times 1/10, 1/10 times 1/9. Remembering as we go down a tree diagram we multiply, and when we get separate branches we add them up to get the overall probability. So this one will be 9/10 times 1/10. So we've got 1/100, 9/100, and 9/100. So 1/100 plus 9/100 plus 9/100 would give us 19/100. Okay, so that's the long-winded way. Now, the other thing is to note that at least once is actually saying that the only other possibility is that Jaspal is not picked at all. So we could do this one and do 1 minus 9/10 times 9/10, because that's the only other possibility. So that's 1 minus 81/100. And that would also give us 19/100, so that would be a lot quicker. And if you know that method, you don't even need to draw a tree diagram. On Tuesday, the computer chooses 2 names, but this time they cannot be chosen twice. So our tree diagram is slightly modified. It's what we call dependent probability. It's depending on what's happened before. So what's happened before, we still want to work out probably that Jaspal is chosen. It doesn't say at least once, it just says chosen, because it can only be chosen once, because you can't pick the same name out twice. So if you go down the first tree, 1/10 probability picking Jaspal, then you stop because nothing else can happen. I could do the next possibility, which is not Jaspal, but it's going to be 9 out of 9. So that's just going to be 1, so it's just 1/10 for that branch. And then Jaspal, not Jaspal. Now the probability is changing, it's going down, because now there are still 1 Jaspal, but there's only 9 people in total because 1's been picked already. It can't be picked again. And there are 8 people left that are not Jaspal. So again, we want these 2. We can work out those 2 and add them up, or we could work out this one and take away from 1. So we've got the 1/10 from the first one plus 9/10 times 1/9, which is 1/10 plus 9/90. 1/10 is 9/90 plus 9/90 is 18/90. That does cancel down, but we don't need to in a probability question. Or we could do 1 minus this possibility, which is the one where Jaspal doesn't get chosen, which is 1 minus 9 over 10 times 8 over 9. That's a slightly easier question to work out. It still gives you the same answer. Okay. Need to speed up a bit. Explain why the probability of the male baby is 2/3, so twice as likely males, females is on a ratio of 2 to 1, so the probability is 2/3 to 1/3. One of these animals expecting 2 babies complete two tree diagrams, so 2/3, 1/3, 2/3, 1/3, 2/3, 1/3. The scientist wants to predict the likely outcome, so we've got to work out the probability being the same. So the same is male, which is 2/3 times 2/3, and female, 1/3 times 1/3. So that's 4/3, 4/9 plus 1/9, which is 5/9. So the same as 5/9, so different is going to be 1 minus 5/9, which is 4/9. So more likely the same. Okay, coin question. Total amount of money is less than 50p, so we could have a 1, 2, a 5, a 10 or a 20p coin. Can't have a 50p coin because that would make a total more than 50. Work out the probability of one of the coins is 10. Exactly one of the coins is 10p. Assume they're all equally likely. Now with this sort of thing, it's very tempting to start off going 1, 2, 5, 10, 20. That's going to be really messy. What we actually want is just the fact it's either 10p or it's not 10p. So we go 10p or not 10. Not interested in all the others, just 10p, not 10. 10p, not 10. So the probability of 10p on the first time is 1 out of 5, because there are 5 coins that are possible. The probability that it's 10p the second time, sorry, the first time is 4 out of 5. So the second coin could also be 1 out of 5, 4 out of 5, 1 out of 5, 4 out of 5. So exactly one of the coins is 10p is this one and this one. So that's 1/5 times 4/5 is 4/25, and 4/5 times 1/5, which is also 4/25. We're going to add those two together to give us 8/25. Okay, this is a very involved question that you've got to really think about what's going on here. What possible things can happen? There's a lot of things we could try, so let's just try and break it down. We'll start with the 20p. If Ella takes 20p and gives that to Jaden, okay, then we have Ella's left with 22, Jaden's got 42. So how do we make it so that they're even? There's only one way to do that, and that is for Jaden to give the 10p back to Ella, or give 10p to Ella to make it 32 and 32. If we look at the 10p, if we take off 10p, we've got 32 and 32. There is no way you can give a coin back to make them equal, because they're already equal. If we had 1p to start with, then we'd have 41 and 22. And again, there's nothing that you can give to the other person to make them even again. So the only thing that's going to work is giving 20p the first time and then 10p back. So if we use that as our tree diagram, so what's the probability? It's got 20p, so that's 1/5. 1 out of 5 are 20s. The not 20s are 4/5. Okay, not really interested in that branch, but we're interested in this one. So we're going to give 10p back, or not 10. So the 10p back So when I've got a 20p here, half the coins are 10p, so that's a probability of a half, and half of them are not 10p's. And we want the one where it has them both the same, which is this one here, which is 1/5 times a half, which is 1/10 for 4 marks. Okay. We are asked to show that the probability of choosing the black counter each time is 0.6. So if it's 0.6, then probability of black followed by probability of black equals, I've not drawn that very much, let's rub that out. So the probability of black and probability of black is going to be 0.6 times 0.6, and that is indeed 0.36. We could use the calculator there to show us that, if I'm not sure. .6 times 0.6 is 925, which is 0.36. Work out the probability of choosing 2 white counters. So if the probability of black is 0.6, the probability of white is going to be 0.4. And we're just timesing those together, and that's going to go to 0.16. Just to show you that, in case you're not sure. 0.16. Okay, work out the probability of choosing at least one white counter. So, back to our tree diagram, it's either black or it's white, 0.6, 0.4. And then we've got black or white, 0.6, 0.4. Black or white, 0.6, 0.4. So, at least one white counter, this is the least question, which is this one, and this one. Again, we could work all those out, add them up, or we can do 1 minus the probability of black and the probability of black, because that's the only one that's not at least. We know that's 0.36, so the answer is 0.64. Okay, another shuffling thing where you're moving things across, quite tricky. Calculate the probability that the card picked from the first pack is number 5, and the second pack is also number 5. So it's either 5 or not 5 is what we're interested in here. 5, not 5, 5, not 5. Okay, the probability that's 5 is 1 out of 5, and the probability not 5 is 4 out of 5. If I pick the 5, 1 and add it over here, now the probability is going to be 2 5s out of 1, 2, 3, 4, 5, 6, 7. And this is going to be 5 out of 7 because it must add up to 1. And then if I pick a non-5 and add it to here, then you're going to have 7 cards still, but only one of them is going to be 5, so that's going to be 1 out of 7. And this is going to be 6 out of 7. So the probability they're both 5s is going to be 1/5 times 2/7, which is 2 over 35. Now, this is where it gets tricky. You have to really think about this. The card picked from the first pack of the cards and the card picked from the second pack card have the same number. So we're really going to have to break this down into different things that happen. So if I start with a 1, so can I pick a 1 twice? Well, yes. If I pick the 1 here, it goes over here, then I can pick it again. But the probability of that is going to be 1 out of 5 in the first one, and when it gets moved to here, there's only 1 out of 7 in the second one, so that's 1 over 35. Probability of 2 and a 2. Okay, the 2, I can pick it here, I can take it over here, now there's 2 2's, so I've got 1/5 times 2 over 7, which is 2 over 35. Okay, and then the 3, the 4 and the 5 are also going to be equal to 2 over 35 each because they're all going to double up. But I can't pick a 6 twice and I can't pick a 7 twice because there isn't one in the first pack. So these are the only possibilities. So I've got 1 and 1, 2, 3, 4 lots of 2 35ths. 4 times 2 35ths is 8/35, plus the 1/35 makes 9/35. Okay, it takes a bit of time to think of how to do that, but that is the best way I can think of it.